All right, hello, welcome to today's class. I have some slides ready for you as well this time. So let's get started, but before that, a few mechanics. I've gone through your first assignment. Most of the things have been done correctly. There's slight modification that I've noticed in the naive-based classification written exercise that could have been implemented. So I will send you my version of the written answer as well. But you got your answer almost correct, most of you. As far as assignment 2 goes, I got the assignments from everybody, all 4 of you. So like I said, the last question of the assignment 2 that I received was basically for you to come up with some questions that you would have, that you would like to ask, as far as the syllabus for that week went. So there are some interesting questions and very good ones as well. So we can go over that towards the end of the call too. You know what? I'll actually go over them right now quickly. So from Tirumala, so we have a difference between regression and classification problems. Good point. If logistic regression is a classification algorithm, which it actually is in terms of how it is used, why is it called logistic regression? So that's a good point. How do I determine which formula to use in the GLM function in R, like how many and which columns to use? Okay. So basically, logistic regression is indeed used for classification. It is called regression because in a sense, classification can be considered as a special case of regression. It is a special case because you're restricting your output values to be categorical or like a class variable instead of being numerical. So that's the only difference. How do you determine which formula to use and how many in which columns? So that's a good point. That's something that we would cover in another class in our syllabus. It's called feature selection. So the question is, how do you decide which one to use? But for now, a good decision could be made just based on your mean square error in terms of regression. But since this is logistic regression, we're going to look at the confusion matrix that I was talking about last time. So the false positives, false negatives, true positives, and true negatives. And there's also some more amount of pipeline that the modeling should go through, which you would learn in today's class. So after that, we'd be in a good shape for doing this for the most part for the third one. So this is from Manish. The logistic regression is susceptible to overfitting and underfitting, so we can consider the parameters based on the summary function in R. But is there any method to consider the best variables among? So similar question. And also he has included the topic of overfitting and underfitting, which is the topic of today's class. So we'd be covering this today. And in terms of how we select the best variables, like I said, it needs to be your classification metric that you would use. And then the right way to evaluate is also important so that you're not evaluating in the wrong way. So we're going to cover this in today's class actually. What if we have a data set with more than 3 outcome variables, and how do we encode the data as we used 0? Okay, in that case, what you would do is known as a multinomial logistic regression. So not the logistic regression is based on a GLM with a binomial assumption, with a Bernoulli assumption, which is only 0 and 1. But if you want to predict 3 classes, right? Like maybe the output is rich, poor, middle class. You want to figure that out just by looking at maybe some variables that tell them about their demographics, where they're living and what they do, where they work and stuff. So if you had 3 or more, then it's called multinomial logistic regression. There are other techniques too, but multinomial logistic regression is the logistic regression version for 3 or more variables. Okay.
Pranit, one more thing, like you have these encodings like one-hot encoding and all that. Do we use them? Like, I mean,
if it was for the variables, yes.
Yeah.
Not for the variable.
Okay.
Yeah. Cool. Okay. So moving on, let's go to. Let's see if this has questions too. So yeah, I mean, there's no specific question on this yet. So, all right, so let's keep going ahead with the content of the class. Let me open my slides in here.
Yeah. Hi, Praneeth. This is Manidip.
Yes.
Yeah, before we go to today's class, can you just rewind this likelihood?
Oh, good point. All right, great point.
Yeah, all the week we have went through theoretical of multiple regression, logistic, and Poisson,
Mhm.
but not this likelihood, and it seems to be a little confused here.
No, it's a very important concept. It's kind of mathematical as well. So I'm glad you asked that question. So let's do that first.
Pranit, I also have one more question.
Okay, go ahead now.
So in a data set, if we have some values which we will like we have some x values and some the one that we have to predict.
Mhm.
So what if we don't have the right set of x? We might not have some values for some columns for some rows, right? There might be some missing data, some data that is not actually right. Like maybe we have a column that is integer, but it does have some string values or something that is not to be there. So what do we do if we have some not the right data to determine why?
Yes. So yeah, not having the right data is kind of a little more generic. Many different issues can happen, but there's a very specific question as well, which is important that you ask, which is if you have missing value entries, right? How do you deal with that? Which is also a part of the not being the right data. So if you have missing values, there is a pre-processing routine. It's called data imputation. There are multiple techniques to deal with that. So we apply those imputation algorithms, and they're going to estimate to their best possibility on what those missing values would have been. So we would populate with those entries so that there would not be any more missing values after the imputation has been done. And then you pass it through your standard pipeline of beginning to predict with the model that you choose, the training and testing, and more than that we're going to do in today's class. So as far as the imputation goes, there are a couple techniques. So there's one called KNearest neighbor imputation, KNN. It's one of the more basic naive methods where what they do is follows. So from a cartoon perspective, this was your data set, and this was the last column. The last column that you want to predict is here, and there's a bunch of columns in here.
Can you share your screen?
Cannot see your screen.
Yes, so let's do that. Hold on. All right, I think you should be able to see my screen now. So yeah, I was giving you a cartoon representation of the imputation for the KNN, K-nearest neighbor imputation, the workings of that algorithm. So if this was your data set and if this was your last column, that is the column that you want to predict, and assume there are a bunch of columns in here. So for the sake of it, I can just draw them. So say you had 1, 2, 3, 4 input columns and 1 output column here in the last one. And say, let's put in some missing values. So let's say this was missing. Let's say this was missing. This was missing. And of course, you would have a lot more rows in here. I just drew 3 rows for now. So what people would do is the follows. So in KNN imputation, if you're dealing with the missing value in this row, these are the entries that you have, right? So what it does is it tries to find k-nearest neighbors of this row in the rest of the data set. So maybe based on what values you already have. So there's no way you can compare here because you don't know if it's near or not, but based on the rest of the values. So maybe this row is among the k-nearest neighbors. Among the k could be 5 nearest neighbors, and some row here, and then some row here. So you have in some other row here, and some other row down in the data set. Okay, so this is like a continuation of the data set. And then what they would do is they would try to find which of the rows in your nearest neighbors do not have a missing value in this particular variable's entry. So this is your third variable, and maybe some of your nearest neighbors do not have a missing entry here. So maybe they do have entries here. And then take an average of that value, and then they put it in here as an imputation for this first row. Then they do the same thing. Now they go to the second row. They try to find the rest of the rows in the data set where the rest of the variables are as close as possible so that you have nearest neighbors that you get. And then you take the entries from the non-missing values in the nearest neighbor set, you average them, and then you put it here as your estimate of what this missing value should have been. So that's the logic of this naive algorithm. Then there's a lot more complicated techniques. There's one called soft impute. It was developed by the authors of a very popular machine learning book. It's called The Elements of Statistical Learning. The authors are from Stanford. They're really popular in the machine learning field. So their technique is called soft impute, but they have a more complicated way to do things. And most of these complicated version of the imputation algorithms, they try to assume that your missing value is a response variable, and then they want to predict it using the rest of the variables. Looking at the set of samples or rows where you do not have missing values, that would be your training data, and then these would be your test data. So there's a lot of internal complicated designs you can come up with. There are more than, I can easily name more than 10 algorithms in the imputation setup. But KNN works very well. Then the question is, how do you choose K? Am I supposed to look at 5 neighbors or 10 neighbors, 20 neighbors? Now that's part of a discussion that would happen in today's class as to how we choose any parameter as part of any of the pipeline that you have to deal with. So the other question was on the likelihood, so let's do that too. Let me clear this up a little bit. Okay, so coming back to real basics of some statistical concepts, we went through what is known as a probability density function or a distribution function. What it is as follows. If your x-axis was your random variable that takes different values, and then your y-axis, if it was the probability density function, which is represented by f, small f in general, f of x is what this is. This is always going to be between 0 and 1, so you have a probability on your y-axis. So this is between 0 and 1. And so if your random variable was 5, then what is the probability of it being 5 is what your y-axis is telling you. That's the probability density function. Now, if you zoom into this a little more, so for example, for a Gaussian random variable, which is very popular, the shape of this is going to be like a bell curve for some specific given parameters. So let me zoom into this view a little more. That will take you to the likelihood view. To be very specific, if you look at the proper formula or the equation for any given density function, so for Gaussian, you have a particular formula for the density function. For binomial, you have a specific formula. So it's a mathematical function. If you look at it, what it will really have is not just being a function of x, but it's going to be a function of x given, this is just a given symbol, given some parameters. And usually the parameters are called the mean, the variance, the standard deviation, or the variance, if you do square of it. But so you would have a set of parameters. So we can call this the parameter set, basically, so theta. So this is what your equation would be. To be very specific, if you want to see an example of this, let's go to our favorite wiki Gaussian distribution. 1 by root 2 pi sigma e power minus x minus mu squared by 2 sigma squared is what it is. So let me show you instead of just blurting some formula. So this is the probability density function of a Gaussian random variable. The Gaussian random variable, as you see here, looks like this bell curves. And based on your choice of these parameters, so it's a function of x, but based on your choice of mu, which is the mean, and the sigma of that particular Gaussian, the standard deviation, or sigma squared, the variance, you would get a different function. So that is what he's showing here. So if your mu was 0 and variance was 0.2, you have this blue Gaussian random variable distribution function. For mu 0, if sigma kept varying, you have these different versions. So if you see as sigma is increasing, it's getting wider. If it's decreasing, it gets shorter because it's the variance around the mean. And there's one with a mu -2, which is this green guy. So the mean is here now. So that is the Gaussian random variable. Now this concept expands to any distribution function, so which is the central point here. Your function is always a function of your random variable, but it depends upon the fact that you're given what its mean and sigma is supposed to be. Is mu 1, is sigma 7, mu 3000, sigma 2, what is it? So that is the theta parameters that decides it. Now this is the PDF function. Okay. Now as far as the likelihood goes, it goes the other way around, which is the formula would still be the same. It would be still the same equation, but you would consider a likelihood as follows. What changes in the equation as follows? The known and unknown unknown variables change. So here the unknown it was a function of x, that is what I mean by known and unknown. And these are the given variables. So likelihood is the same equation, but it is considered as a function of the parameters given your data. Your data is the random variable, basically. Okay, don't be bugged by this arrow. Okay, yeah, so there we go. So it's the same formula. So the likelihood for normal distribution is exactly the same formula as its probability density function, which is this one. But in PDF, it's a function of x. In likelihood, it's a x given mu theta is what it is. So PDF is a function of x given mu and theta. Likelihood is the same equation, but it's a function of mu and theta, mu and sigma, which is known as the theta parameters. It's a function of mu and sigma given your x. That's the only difference. Now, as far as why and how it's a useful function, why is it so coming up every time is as follows. So this is the definition of the likelihood. You only have the definition. Like PDF, you still have some, apart from definition, you have some intuition what it is. It's giving you the probability of that occurring, that event occurring, as any given value is what it is. So let's get some intuition for the likelihood as well. And by the way, as far as the bigger bucket of where this concept falls under, it does fall in statistics, obviously, but there's a topic called statistical inference. It's a full-level graduate course in most stat departments. So that's where people study likelihood and how to use likelihood and all that a lot more. So let's come up with why. Let's go ahead now with the likelihood a little more so you get some more understanding about it. It's a very important concept, actually. So say I first give you data, right? Now let's assume it is data of distribution of heights of the kids in class 4, of children in class 4. So if I just plot the heights on the x-axis, on the y-axis of various children as a histogram. So here the x-axis is not a proper axis, just like an index. So I'm just binning up the heights here. So if this was the distribution of the heights, right? And if you use the distribution, you can always, there are functions in R and packages called density that will try to estimate looking at the histogram, which is the counts of heights. So if you had 10 counts of heights of this amount, and these many have 4 feet, and these many have 4 or 5, these many have 3 feet, whatever it is. So you can always convert it into a probability density function. This is just not to deviate from the discussion, just to give you a hint. People do use this a lot of times. It's just like a trick. If you have a histogram of raw data, you can come up with a density function using a technique called kernel density estimation, KDE. Kernel density estimation. In R, the function is called density. If you pass it a histogram, it will give you a density. So it will give you a density function like this. Okay. So basically, all I'm telling is, even if you did not use that, you can estimate the density function by counting what is the probability of getting height equal to 3 feet in a class of 60 people. So you would count, 20 people are 3 feet in a class of 60 people, so the probability is 20 by 60. So you can do this in a raw fashion computationally as well. You don't have to use this automatic function to estimate that. So the thing is, if you have some random variable that you're measuring, you would also have a distribution. Either way, whatever the approach you take, it's already there in the data. You just have to compute it. So now you have a distribution, which kind of looks like a bell curve, right? So now this is going from data to the distribution directly. Now, if you had a very complicated thing set up a little more. Actually, before we go to a complicated thing, now let's answer a different question. I give you again the same data, but you don't know what the mu and theta of your distribution function is supposed to be. So you know that it is a Gaussian distribution if I give you that assumption. The question is, which of the mu and theta am I supposed to use? Because here I chose 4 different choices of mu theta, and I have 4 different Gaussian functions, Gaussian distribution functions. Now the question is, I have a density that I've chosen in terms of what family it is. I've chosen that f has to be Gaussian. So you know the equation now. You know that it's a function of x given mu theta. Now the question is, what mu and theta, or what mu and sigma is going to fit the data the most? So am I supposed to go with this distribution, this distribution, this distribution, or this distribution? Which distribution do I go with? So basically, which means which parameters of mu and sigma of Gaussian am I supposed to choose so that it explains the heights of children in class 4 as well as possible. So that then you can literally use that as a way to describe the density of distributions of people in your class, in the class 4, right? So that question needs to be answered. So now you're asking, I know the equation of f. I know the formula of f being looking like this for Gaussian, since I chose Gaussian as my choice of distributions. Now the question is, I have a data points. I have heights of different children. Now I want to know what is the theta that will give me a particular distribution of Gaussian that will fit my data the most. So ideally you need theta, mu and sigma that fits your data the most, like this. So you need to figure that out, right? So there needs to be a way to do it. You cannot just try all possible mu and sigmas, because it's really hard to figure out the mu and sigma that perfectly fits the data the best possible. Like they're like infinite possibilities, because mu and sigma literally can be anywhere on the number line, as long as it's not like infinity. Like it needs to be some finite number. It could be decimal, any decimal of mu and sigma. So you can have like millions of curves. How do you know which density explains my distribution of children the most? So there you write down this function, which you have a complete equation of, and you know that thetas are your unknown now, and x's are given to you. So what you then do is you try to maximize the likelihood of this function. But then the question is, let's zoom in a little more now. Your x's are not 1x. You don't have one height. Your x is literally heights of n students, 1 to n, right? So for any given x, you have the likelihood as a function of theta that you don't know, given that particular x1. Then there's a function of theta given x2. Now in statistics, there is a concept called independent and identically distributed, IID. It's very, very popular notion. They literally call it IID, which means the follows. So it basically tells us if you have this data set, the assumption we are making are two assumptions. One is we're assuming that it is Gaussian distributed before we made this discussion. So we decided that the function has to look like a Gaussian distribution function, or the Gaussian likelihood function. So identically distributed. We're assuming every height can be modeled by Gaussian distribution. It's coming from a Gaussian distribution. We don't know if it is this Gaussian, if it is this Gaussian, or if it is this Gaussian, or if it's this Gaussian. That can be known if you literally know exactly the mu and sigma, the theta parameters that go into that Gaussian. So at least you're assuming it's identical. So I'm not assuming that one height is sampled from Gaussian, another height is sampled from Poisson. I'm not saying that. You could have done that, but that's not what the point of this particular likelihood lesson is that we're taking here. So now independent means the class, we're assuming that the height of one person, one kid, does not depend on the height of the other kid. That is an assumption which is fair to make unless there's all 60 kids coming from the same parents in the same class. Then there could be a lot of genetic, a dependency between the height of my height depending on the height of my brother's height in my class or my sister's height. But that's not what we're assuming. And it's a very fair assumption for heights of a kid. It's very likely that they're independent of one kid's height is independent of the other, in a sense. So basically you have some Gaussian distribution. You know what mu and theta it is coming from. So you know the exact curve it is coming from, and each kid is being sampled from that curve. So some kids will be in the tail, the ones that are less probable. So these are low probability events because the probability is low. It's not high. These are the high probability events. So most kids would end up being in this height. The tail kids, which are like the shorter ones, the outliers would be of this height. The ones that are super tall are going to be this height as far as their peer group in the fourth grade goes. So that's the assumption. Under this assumption, we know what the formula for the Gaussian function is. We know that it's, now we are assuming it as a function of theta, the mu and sigma that we don't know, and given your data set x1 to xn. So since you assumed IID, if you remember now, let me do a screenshot of this, by the way. I can send this to you right after the class. It'll be with me. Is everyone with me till where I am right now? Any questions at this point? And then now you will completely figure out why likelihood is useful. So I told you what is the definition of likelihood. I'm just going into giving you an intuition of why it is extremely useful in this situation, which will happen in another minute or two. But any questions on what is on the board here right now? It's okay if you don't have questions, but if any questions, I don't want to miss the opportunity. Okay, so yeah, go ahead.
So you said there will be multiple Gaussians in a class, right? So you told that. So All of them are independents, right? Independent events. So one refers to the height or one may refers to the another event like that.
Mm-hmm.
So why it is difficult to pick a Gaussian, like if you are calculating the only height of the kids,
Mm-hmm.
we'll have only one curve.
You will not have one curve. The question is the follows. So let me clear the screen. You can estimate one curve, which is true, which is the histogram kind of concept, right? You can estimate this curve, all right? But if you want to do it mathematically, how would you do that? How would you know if the function is looking like 1 by 2 pi root sigma, you know, the complicated function in here? How would you know automatically? What would be a process where you can automatically estimate the mu and sigma? Like, can you write a function in R that will take the heights of kids and automatically give me what mu and sigma the Gaussian is coming from? Right? So there's two ways of doing it. What you're saying is you're looking from an intuitive point, you're saying there is this curve I can probably fit by doing some smoothing or fitting a histogram or doing some KDE. But that's not going to give you, that's going to give you the curve. It's not going to give you the mu and sigma that is generating that curve. So it could be even more complicated. If your data set was coming from a mixture of two Gaussians. So if your data set was literally alpha times x1, which is a Gaussian random variable, plus alpha 2 times x2, which is another Gaussian random variable, where alpha 1 and alpha 2 are numbers between 0 and 1, but they sum up to 1. So this could be 0.3, this could be 0.7. And then I come up with a data set that would look not as simple as a bell curve. It will look like that. And then it will look again small like here. And then there might be a smaller height here. So you have two peaks of different lengths. So if I just give you the data, I'm sure you can fit some approximate curve like this, but how will you know what is the mu and sigma of x1 and x2, right? Same thing. In logistic regression, you're assuming your response is binomially distributed, right? So you're assuming your y, or to be even specific, okay, yeah, let's assume y is binomially distributed. So you're assuming y is equal to exponential of x beta, which is x1 beta 1 plus x2 beta 2. And then I'm assuming that the y is your outputs. Your x's are real numbers. Your outputs are Bernoulli distributed. So if you did an expectation of y, which is the mean of y, then it would have to be of an equation of n times p, because that is the formula for a Bernoulli distributed mean. An expectation means mean. So if this is what you're measuring, and x's are not like just one variable like here. Now you have like 10 x variables. You have like a 10-dimensional x as your input. And then there is some linear combination with betas, and there's this exponential. There's this complicated function that you need to make sure it ends up as being a binomial, but you need to know what is the particular p of that binomial, because p is the parameter of a binomial distribution. You need to know p and you need to know n as well. So how do you know what, given your data set, say the data set that I gave you for your assignment, how can you tell me what p would estimate the distribution for each y correctly? And if I can make it even complicated. If I said each y was coming with a distribution of a different p, so y is coming from a binomial of p1, y2 can be a binomial of p2, where p1 and p2 can be completely different. How do you estimate the vector of p's? You know, so the point is the simpler example of heights I gave you is for teaching purposes at the simplest level as an example. But as I keep making this stochastic modeling function harder and harder, it's truly impossible for manually coming up with a way to check all the infinite possibilities of what the p would be, or what the mu and sigma would be. So that's the bigger point there. Does that answer your question? Or do you still think that you do have a way that you can come up with the parameter?
Yeah, I'm somewhat good in it, yeah.
Yeah, I mean, yeah, you definitely have to think through this a little more. I'm not saying you have to get it right away. So this is just the material. So that's the point. Now the question is, you have likelihood as a function of your data, of your parameter, given data. Now, in your logistic regression, so and then your data is n independent points. It's not one point. So if you come to your basic probability laws, if your random variables are independent, your joint probability of two random variables x comma y that are independent is equal to the probability of x, just the marginal probability of just the x, times the probability of y, right? And then to be very specific on the notation, these three f's are not the same f's. So here people write x, y again, just to say it's a joint probability of x. And here they put fx, which means it's a density function of x. And here they put y. That's the reason you have fy of y. So it's a density function of y. So the fx, fy, f subscript s, f subscript y, f subscript x, y are different functions. So this is the probability law. If you have a joint probability, it's going to be a product of your marginals. So what happens in likelihood is the follows. Your likelihood function, if I were to expand this, what I do is I take the Gaussian formula, which is this, and then I write it as f of theta, that is unknown, of course, which is what we want to estimate, given x1 times f of theta given x2, and so on till f of theta given xn, which is your n samples that you have, right? For each height, you want to know what is the likelihood function for that particular distribution. Now, in this formula, what people do, this is known as the likelihood function. So you can literally write this down. If I were to give you like a homework of, can you write down the equation for the likelihood of in this setting for a Gaussian random variable, you literally have to write this formula down and write it as a product. So this is basically a product. So sigma is a symbol for, in math, for summation. The pi is not only the symbol for the popular pi, but also a symbol for a product. So likelihood function is pi equal to 1 to n f of theta given xi. So if I were to write this down in a shorter notation, this is the same as this. So now, what is a maximum likelihood estimator? It is an estimate of theta that would maximize this function. So you're optimizing this product function and trying to find a theta belonging to the real numbers space. It could be any real number. So you're supposed to search so that you maximize this. Now, maximizing products is a little difficult because it's not like as simple as a convex function. It's not as simple as this or this, where you say the maxima is here or here. The function could be very complicated. It could be like this, like this. You have many local maximas, and you have a global maxima, that kind of stuff. And you don't know where it is because it's a very complicated function. And x's are not just one-dimensional. You have a very high-dimensional function. So what people do is they apply a log on this. So when you apply a log of the products, what would happen is it would become a log of the individual sums. That's the property of the log. That's the property of the logarithm. So you have a sum of, so it's called the log likelihood. So you can search for log likelihood logistic regression. That's what they would use. They would apply, they come up with the log likelihood function. They apply the logarithm to it. So the product becomes a set of sums. So you have a set of sums of log functions. Log of theta x given x1 plus log of theta given x2 and so on. Log of the likelihood of, so log of likelihood of theta given x1 and so on. So the thing is, now you want to figure out which theta maximizes this log likelihood or which theta maximizes this just likelihood. So that you want to have the particular theta that maximizes the likelihood of your data being observed for that theta. So I want to figure out if theta were 1 and theta, sigma were 3, would it have been most likelihood that my data came from that distribution? Or if it is the fact that is theta 5 and sigma equal to 0 or sigma equal to 0.1. So you want to figure out for what combination of thetas, what particular set of thetas, your data seems to be most likely for having come from that particular distribution of Gaussian that you chose. So this function is now literally maximized using the derivatives and all that kind of stuff. There's a lot of optimization functions that you could use to maximize this. So the solution of that optimization routine will be the theta that will maximize this log likelihood. And that will tell you what sigma and mu that your data came from the most. So this is the abstract question. Now, the same thing is being done for your logistic regression. So, or even for your linear regression, you can also come up with a log likelihood version of the solution. Or any regression question that you have some distributional assumptions on. So anything in the generalized linear model family has a distributional assumption on your response. So you have a maximum log likelihood. All you want to estimate is the parameters. Once you have the parameters, you have the best fit. So whenever you're running your thing in R, what it's doing is it's writing down this likelihood function, and it's maximizing the parameters, and based on that, you're getting the best fit of what your coefficients should have been. So that's the concept of likelihood. This is a full-level topic in grad course at the master's and PhD level. So it is a very lengthy concept. It's very powerful and useful in estimating any parameter. So the problem of statistical inference is to estimate parameters given the data, given you have some distributional statistical assumptions. Whenever you have a statistical assumption, you would have some parameters. Because whenever there's a statistical assumption, there's a distribution function, and every distribution function has some parameters, and you don't know what the parameters is. All you know is the data. So as soon as I give you the data and I give you the model that I'm fitting, there's unknown parameters which are estimated using the maximum likelihood estimator, which is maximizing this. Any questions on this? This basically completes the curve on what I was trying to explain in terms of the likelihood. Any questions at this point right away, or you can come with it later today?
Yes. When we did this log function on the in our previous assignment, we are getting few values. So this should be small, or like how do we predict it from there?
Oh, I saw your assignment. I know you sent it this today. I think so. Then probably I saw one person did compute the likelihood. You wrote some exponential function, right? A function of using some exponential. Is that correct? Well, you, I guess. So what is the exact question now when you say small and big? Ideally, if you're literally computing the log likelihood of your logistic regression model, it has to be as large as possible.
Okay.
Sometimes some people compute the negative log likelihood. Then you have to minimize it because you put the negative. Maximization of a negative function is equal to maximization of function.
Okay. And the other question is, like, rather than doing this likelihood, can we just plot a graph with the results that we get, and can we?
This is open-ended. You can definitely do that. I mean, it will definitely be appreciated. Yeah, you can do your diggings and learnings with it as much as possible. Yeah, it's a concrete abstract concept.
Okay.
Stay with it as much as
Thanks.
All right. So let's. Go ahead. Okay.
Do we have any example where you can give us where we can practice this likelihood function using all those theoretical concepts? And I mean, we had it in the last example though, but anything that you would suggest?
Yeah, the last example was more from a computational, just using some softwares and stuff, not to really compute it, right? The assignment, the goal was not that. It happened internally when you ran the out function. So there is a trade-off. If you're definitely interested in this kind of stuff, because I'm trained both in the math side of things and on the computational side. If you're interested in these things, I'll be happy to give you a minor assignment and also give you a lot of reading notes actually in it.
That would work out.
Yeah. So if you remember the steps, just to revise though, I give you the distribution that I'm choosing. So it could be Gaussian or Bernoulli or Poisson, whatever it is. And then you know what the formula is, because the distribution, every distribution has a formula for the PDF. All you have to do to compute likelihood given the data is do this. Write it as a product of the densities for each data point as a function of theta. And then you have this.
Okay.
And then plot it as a function of theta and see at what theta it looks like the maximum, that kind of thing. Or you can use an optimization function on what you wrote. There's optimization routines. You can pass this function that you encode into that optimization routine. Then it will automatically give you at this particular theta, your function would be maximum. That kind of thing. So yeah, we can do that. We can definitely do that. Yeah.
Sure.
You can make it as complicated as possible, but the point of this course is not to give you a PhD in mathematical statistics, right? There's a trade-off.
Yeah,
between learning the right concepts, but also getting some practical knowledge. Because it's a boot camp. I mean, boot camp is short, so I can never go into a boot camp and say I did a 3-month boot camp and now I'm a quantum physicist. You don't become anything in 3 months through a boot camp. It's over a period of time, but these boot camps are very useful because they're giving the right direction. They're showing you what the contents of the topics are. They're explaining parts of the direction. They're also helping you get a job, that kind of thing. So it's a learning process that you keep on learning more and more after the bootcamp as well. But we can do that. All right, so now let's go into the slides. So let me do a quick snapshot of this. Like Heyman said, we're going to have a nice writing pad where I can literally write on my side. It's going to show up digitally. Right now I'm writing with my mouse and it's really hard to write it clearly. Okay, so I will send you these afterwards. Now the screen is still being shared, so let me open up something here. So the topic of today's lecture is more about generalization, which is kind of pointing to making sure that your machine learning model that you're fitting, the supervised model, like logistic regression or other things that you learn in the future, is not overfitting or underfitting. Like, am I using too complicated a fit or too simple a fit? And what is overfitting and underfitting? How do we quantify it and all these kind of things? So let's start with that. This is your standard setup. You can see my screen, right, everybody? Yes, I think you should, yeah. Okay, yeah. So just to make sure we have the terminology right, your X is your feature set. So you have P predictors, N samples, N by P. Y is your label set. You again have N labels. And you can have K equal to 1, which is the standard setup where you have one response, one label per record of your input. Okay, so as far as the whole, the history goes, like Gauss did this 190 years ago, which is the y minus x beta. He came up with a solution for linear regression, which gives you the best linear fit. So he knew a solution for what the betas are supposed to be, which is linear regression. Now we moved a lot further than that, which is our generalized linear model, where you're modeling the expectation of each given response variable. But on average, what is your response supposed to be? What am I supposed to predict on average with most likelihood? Such that it can be modeled as this function, where G inverse is exponential in the case of Poisson distribution. It is a logit function in the case of binomial distribution, and so on and so forth. So you have some distributional assumption on your F. So you're modeling your prediction as a sum of those functions. And in this particular case, your Fi of xi is going to be xi times beta 1. But Fi could have been a little more complicated. So if it was a different kind of a complicated function, instead of just x beta, like whatever is inside, you'd have, so a special case is x beta. So x1 beta 1 plus x2 beta 2 plus x3 beta 3, that's what the sigma is. And then you apply a logit function, and then you get the prediction that you're modeling for a binomial in a logistic regression. But your F need not be x beta 1. It could have been a complicated function. It could have been some nonlinear function of x1 plus some complicated function of x2. So you're summing up complicated functions of each individual feature input variable that you're getting to try to predict your output, which is known as the generalized additive model. So if you have gone one step ahead, which is GLM, so linear regression is a special case of GLM. GLM is a special case of generalized additive model, where your F could be not x beta 1 that you're using trying to predict. So this is not x beta 1. It's a very complicated function of x1 plus a complicated function of x2 plus so on. And this is supposed to be k, because p actually, not n, because you're summing in p variables actually. So let's change this. This was a tutorial I gave in Atlanta 3 years ago. Anyway, so if you did something like that in the generalized additive model, what you would be fitting is for each input variable. So this was your first feature, second feature, third feature. Say you had 4 features. You're fitting a nonlinear function. So you got 3 answers for some particular data set, so that when I sum up this function plus this function plus this function plus this function. So for example, at 0, this is 0, this is kind of close to 1, this is 0, this is 0. So you get 0 as a sum. But at 0.2, I get 1. If this was 0.2, then I get 1 plus 8 or 7.5 plus 1.5 plus 0 is going to be the prediction for my output, you know? So, but if I can do something more complicated, if my first variable was 0.2 in the first record, and my second variable was 0.6 in the first record, so then you have 1 plus whatever is at 0.6, so 1 plus 4, and if my third variable was 0.4 plus 4, if fourth variable is 1 plus 0, that will give me the prediction. So for whatever combination, if my first variable was some amount, the second variable was some amount, third variable was some amount, I sum those 4 functions, then I get my prediction. So that's the generalized additive model. This was brought up by Peep Shirani as well, the others from Stanford Statistics Department of The Elements of Statistical Machine Learning, a very popular book for machine learning. So this is the generalized additive model. And even here, you have a concept of likelihood, because if this was Bernoulli, all you're changing is f is not x beta anymore. F is a complicated function that they're fitting. So even here, you would have a likelihood that you can write for yi. You would have a log likelihood function you can literally write out, because you know that there's a distributional function. You're writing those products. You will have a very complicated log likelihood function that when you optimize, you will automatically get what your thetas and your outputs, your predictions are supposed to be. What your f's would be learned by that, your predictions would be learned by that as a result of it. So this is generalized additive model. I'm going to give you a small assignment on this as well. It's going to be, from a computational standpoint, just like GLM, you're going to use the GAM function. It comes from a package called MGCV. You'll get those details, and then you're going to apply generalized additive model version of your prediction. And you would see how it would do better or the same as logistic regression that you tried for the same data set. So now the question, if you look from a big standpoint, it's all about finding some mapping. It could be linear regression that goes from X input to your output Y. It could be linear, it could be GLM, it could be GAM, it could be SVM, neural network, whatever. It could be a million kinds of functions. And every function would have some parameters, theta, that you're trying to estimate. So if you have some model that you're choosing, and that model will have some thetas, a list of parameters, that if you can choose correctly, then you have the right map that you have defined completely that will give you predictions from X to Y. So obviously, you know what those unknowns are. Here it's F, here it is beta, so on and so forth. You need to find a parameter set correctly for any given model. So this is the setup. You have existing features. This is supervised learning, which you know. You have known labels. You want to build a function from X to Y, which you don't know. There are some assumptions, which would be like, is it the logistic regression model assumption or some other model, or am I using neural network? Those are the assumptions. And you want to build a function that goes from existing features to known labels. And there could be a lot of functions that will go from existing features to known labels in a very good way with less error. It doesn't mean all those functions are good. You want to find only one particular function that goes from X to Y, that when you apply on your unavailable list of features, which you will get in the future, like your company will give this in the future to feed into this, and it will not know what your results should be. And it tries to use your model to assume that you have a good model, so let's believe whatever your model is giving. So you want to choose one that will optimize this prediction loss as good as possible. Your accuracy and prediction should be good in this set, not just in this set. This is your training set. If it's good here, okay, well and good. It's just the observation. It doesn't necessarily mean that if you predict good from here to here, you would also do good prediction from here to here. You don't know. You need to have some guarantee on that. So if it's too good in here and doing very bad in here, then you're overfitting. If it's doing very bad in your training set and still doing good here, then maybe you're underfitting. Maybe you can do still better in the set. Maybe you can improve the complexity here to some extent. So that's the overfitting, underfitting. We're going to study this even more concretely. So f theta x is your regression function that goes from X to Y. So f theta x will give you some prediction of Y, and this is your Y that you already have in your training set. So this is your Y train. This is your predicted Y train from X to Y using your f theta that you learned, which was learned by learning some particular theta that you believe was correct. And then you have a loss function that measures how good your prediction is with respect to Y. So for an example loss in regression is your mean square error. There's supposed to be sigma here and all that, but this is the square error of your residuals of what you predicted. So I'm going to put in that here later. Any questions at this point on where we are heading towards? Are we okay with the speed right now? All right, so I'm assuming we're doing fine. Okay, so let's continue on with where we're going. So now, all the question is about, for a closed-end model F, you would have parameters. You need to find the right parameter, theta. And let me tell you what is underfitting and overfitting now. So say I have a particular model. Let's say I call it a polynomial model. I'm just calling it. And I choose a degree of any given polynomial to decide what my model should be. So if my degree was very low, it would be a simple linear regression. If it was quadratic, then I have a quadratic model. If I have a very high degree polynomial, I have these complicated curves that I'm fitting here, for example. And the question is, if these circular black points are my data set, for example. So that's what I want to predict. there is a lot of curves in here, this tight patch that is going reasonably through the data. Then there is this guy, this violet guy, that's going even more through the data, as he's trying to touch every single data point. There is this red guy, the red function, which is not going through any data point properly. It's just going through this overall pattern like this. Then there's this green that's somewhere in the middle. So there's a combination of functions just based on my choice of degree, which was my parameter in my chosen model. So what parameter do I choose? Do I choose the parameter that gave me the green function, the red function, blue function? Which is the best function to predict? That's the question. Now here, I'm zooming that situation a little more just by showing two functions. I have this data set, then I have this red function, which is highly complicated. It touches every single point in my data set. My red function, prediction function, is going through every single point, explaining every single point in the data set. Then there's my green function that is explaining the overall pattern, but it's missing quite a few. Like, it's not going through all these points, but it's going through this overall pattern. If you kind of go a little ahead and a little back from your screen and see how the shape is, the shape does look like this for your data, if you see. That it's not going through every single data point. Now, which one is better? This is going to give me, the red one is going to give me 0 prediction error. It's going to give me 100% prediction accuracy. It's like a crystal ball in the movies. It's kind of predicting everything correctly. In your training data set, you need to remember on the training data set, your green is not 100% prediction error. It's not close to 5% either. It's like the prediction accuracy is not 100%, not as bad as close to 5% or 1%. It may be somewhere around 85% or 95% prediction accuracy. Okay, now how do we generalize and which one do we choose? Some people might think maybe the red is the right thing to do. It may be very likely that it's probably a very bad thing to choose the red function, because the whole goal is not predicting well on your existing data set, but when you apply it in your test setup, you want to make sure your prediction accuracy is the highest here. Now the red may be performing very bad here and maybe performing very good here. Or it might as well be the case that it's performing good here as well as it's performing good here. But you cannot evaluate how it is performing here because you never know the true label. You only know what it's predicting. You don't know if it's predicting the right thing or not. That thing you can only do in the training set because you know what the true label is. So let's see, how do we answer that question? So this is the question of generalization in machine learning. Yes. Yes.
Predicting data wouldn't rely on predicting the training data.
Sorry, I think you have a valid question. There was some signal that was shaky. Can you say that again now? Now I can listen to my audio correctly.
So predicting the test data should rely on predicting the training data, right? So if we can predict every training data, then it should predict the test data in the right way, right?
That is not necessary. If you're doing very good, I will tell you why now. It's a great question. That's the point of this lecture today. It is not necessary, and I'll give you a reason as well. Okay. Let me give you an intuitive reason, for example. Say I am teaching say I had another younger brother, and say he was in his 10th grade, and I'm teaching him mathematics every day at home, for his mathematics final exam in his 10th grade. Say if I gave him the book of questions, of 10 questions, and I told him, just by heart, just memorize the answers for all these 10 mathematical problems, your practice questions. Okay, so his training set is only 10 questions. I'm not giving him the mathematics textbook. I'm only giving him 10 questions and 10 answers. So that's his training data. I told him, just memorize it. Forget about the concept. Forget about how things work. Forget how you can apply all this. If this was your question, this is supposed to be your answer. I asked him to memorize it. So then I gave him a test on exactly that data, that question paper. After 1 hour, I gave him a test on that. Say my younger brother had a good memory, so he's going to get 100 by 100 on his training set. Now, the test set is a set of questions sampled from the mathematics textbook, not what I trained him on, not my 10 questions. He may be very lucky if one question in his question paper tomorrow in his examination hall exactly matches one of my 10 questions. That thing is going to definitely get right because he memorized it, as long as he doesn't forget it. But the rest of the 9 questions, I will assure you, if I did not train him on anything else, he's going to get 0 out of all those 9 questions. So one thing that matched, because it was like a leak kind of thing that happened, so he got 1 by 10 or 1 by 100 tomorrow. So he performed 100 by 100 percentage, so 10 by 10, which is 100% accuracy on the training set. He got 1 out of 100 in the examination, which is like a fail, right? Like a horrible fail. So that's a a very exact example of what's happening here as well. The point is not to learn everything by heart to your function in your training set. The point is to learn just the right amount. You only want to learn some amount of a generalization. You want to learn the concepts of what go from X to Y. If you learn too much of it, you're not going to do good enough in the future with that particular function. Because this function, if you would see the way it is going up and down, it's very highly variable, the red function. In the future point, if it was somewhere, it's supposed to be here, it might end up getting a prediction here or here or here. It will not be exactly there. But the green function, more likely to at least go close by to the true answer. At least it's a reasonable prediction. You know, it's not going to give you random predictions that are too off. So that's the point of overfitting on a training set and performing horribly in a test set. That's what's happening here. Does that answer your question or give you something to think about some more?
Yes, perfect.
Okay, perfect, good. So that's what's going on here. That's the point. It's not model. The course is called machine learning or statistical modeling. It's not called curve fitting. Fit the best possible curve to the given data set. You want to fit the best possible curve that will predict well in the future. So yeah, we're done with this. So how do we generalize? So we had a loss function which we decided for regression it could be mean square error. Now we have, this is the exact way to write it. So this is the average of prediction errors on all your n samples, which is this average. You want to choose, this is the empirical loss. So this is the loss on your training set, basically. Empirical risk minimization. You want to minimize this on your training set, I agree, but not too much. You want to minimize it exactly. What you really want to minimize is not this. You're just using this as some sort of a proxy, but what you really want to minimize for a model that predicts well in the future is this function, which is this integral, is a summation of your loss. If you knew the distribution from which your questions are coming, from which your training data set, X and Y is being sampled from, there's a joint distribution from which your questions are coming in your test, right? So that is the producer. This is like your mathematics textbook. There's a probability. Some questions are more likely, some less likely. Maybe the more likely ones are the mediocre questions, not too hard, not too easy. Too easy or not too likely. Just like a question like in a 10th class exam, no one will ask you what is 3 plus 1, you know? It's very less likely. So a very highly complicated question, you would not get like a PhD pure mathematics question in 10th class exam. That's very unlikely. So there's some distribution of what is likely based on your choice. If you can model the joint distribution that is producing your x's and y's as good as possible, and for those x's and y's, specifically, if you can, for every given x and y, on average, if you can minimize, if you can come up with a function f that minimizes your loss, so this is the expected loss. If you remember the expectation, the formula of expectation, if you go back to your textbooks, is integral of x is the random variable times probability of x. But here your random variable is a function of two random variables, and it's a random function. Your random variable is L. So here it is integral of your random function, L of x comma y, times the probability of x comma y. So this is the expected loss. This is the true loss you want to minimize. You want to do the best with respect to the book or the concept provider, which is your joint function, not with respect to your data set necessarily. So this is what you truly are going for. So this is just hitting on different kinds of functions you can, I don't want to go through this too much right now. So now there is a parametric characterization of the mapping regression function you're learning. So if you're learning a linear regression, you always have parameters. That's what I'm saying in here. If you're learning a linear regression, you want to learn slope and intercept. If you're learning a spline function, we've not discussed this. These are spline functions. The question is, what they do in splines is they try to fix some points of your curve and allow the rest of the curve to be wiggly and be nonlinear and vary. So the question is, how many knots, how many points do I fix, and where do I fix those functions? That is the cubic spline. There is a proper mathematical function. If you search cubic spline, you'll get it. There's nearest neighbor regression where my prediction for any output x is going to be, I'm going to find the nearest neighbors of x's in my training data. So if I have a test x, I'll find that nearest neighbors of that, k nearest neighbors of that particular x in the test data in my training data, and then I will see what the corresponding responses were. I would average those responses. I would produce that as my prediction for my test x. So there the question is, how many nearest neighbors am I supposed to use? That's the parameter. For any given technique, so we've not gone through these techniques, which will go in the future. SVM, random forest, every technique, right from linear regression to this and maybe 100 more techniques I can mention here, always will have some parameters you need to choose. Some parameters will give you very complicated functions like the red one. Some will give you right amount of complexity, like green. Some will be underfitting, like the red one here is underfitting. It's doing too bad, and the green is much better, right? So that's underfitting, for example. So you want to choose the parameters so that you're not overfitting or underfitting, but you're optimally fitting. And how is that done? It's done through a process called cross-validation. I will go through this in a little detail next class, but I will do it very quickly now. If this was your training data, you break, and this was your test data, you take your training data and you, I will give, I think I will, I don't want to rush through this. This is a very important concept. I will go through this in the next class or in the cartoon. But this is a better way to explain cross-validation. This is a bigger picture. I don't want to do this right now. Let's do this picture. This is called k-fold cross-validation. This is a way to choose what parameter you need to have so that you're not overfitting or underfitting. So this is the answer to your question, to the question we are concerned here. What is the parameter that is optimally fitting, not under or over? So if this was your training data set, you break it down into k pieces. So your entire training data set is this. I break it down into k pieces of training data. So this is like 10 rows, this is 10 rows, 10 rows. Then I have, if k was 5, then I have 10 times 5, 50 rows in my training. But if I had 1,000 rows in my training, I can have k equal to 5, then I have 200, 200, 200 in each of my 5 splits. And then in the first, we call each of the split a fold. It's just the terminology. In my first split, I drop one chunk out, and then I train on the rest. So basically, I drop one chunk out. So I drop this fold out completely. And then I train on the rest of the fold. So in the first time, my first split of training and data of x, y, I'm putting it aside. I'm using it as my test set. I'm training on the rest of the k folds. And then I get a model that I'm predicting on the first chunk. And the next time I drop this guy, I train on the rest of the folds, and then I predict on the guy I dropped. Third time I drop, so the last time I drop this guy, I train on the rest of the guys, and then I predict on this set. So basically my training set, I'm making sure I'm putting some part of my training set aside, which I'm not using into training the model. But the part that I put aside, I still know what the true answers are for the labels, because it is the training set. So that way I'm making it train on a few things and then testing it in the rest of it, so that you're trying to simulate the situation of what would happen in the future. When you deploy in the future, you would test on something that you did not train on, right? So that's what you're trying to do here. So you would get 5 different errors for each fold. You average those errors. That's known as the cross-validation error. So if this x-axis was the choice of parameter, and say these are some parameters that give you low complex, and the y-axis is the complexity of the fit. So this is giving low complex models. This is giving highly complex models here. The question is, which level of complexity do I choose for optimal fitting, right? Do I need low complex model, high complex model? It depends on your data set. Now, what would happen? Your training error, as you keep increasing the complexity, this dark line would keep on reducing. Your training error will become like perfect. You're like almost memorizing the training data set here. But at that level of complexity, if you see your test error, which is this line, it's going to be horrible. You'll perform very bad on your test set. But you're doing great on the training set. But so this is your cross-validation error. This is not the tester. This is like even better than tester. This is the cross-validation error that came from this process. So for each parameter choice, you have some training error, some cross-validation error. For this parameter, this training. So you want to choose the parameter that will minimize your cross-validation error as much as possible, which is here. This is the level of complexity you want to choose. That may give you this amount of training error, but don't be bothered about it. It's not this high. It's not this low. Don't worry about it, but your cross-validation error is the least. So that's a guarantee that in the future, you would do somewhere around this kind of a performance at least. If you chose a model of lesser complexity, your future performance would go bad. If you choose a higher complexity, your future performance would go bad. So this is overfitting. This is underfitting. This is the right choice of complexity that you want to choose. Okay, so this is the start of overtraining. If you're doing more than this, you're beginning to overtrain or overfit, basically. This was from a textbook. This is from the Statistical Learning Theory by Thiep Shrani from Stanford. This is what I simulated myself. This is from R. I choose some polynomial model, and then I was trying to choose the degree of polynomial, and I could literally see this. In reality, I was fitting complex polynomials, which is how I generated these plots, by the way, personally, and stuff. So this is the plot of the cross-validation error and the training error. My training error kept on reducing, like I explained 100% of my training set, but my cross-validation error reduced till here. So basically, a degree of polynomial 1 is the best predictor for the future. Anything more is overfitting, less is underfitting, because the dotted line is the cross-validation error. All right, so there's a long list of techniques. Most techniques have tuning parameters. We can out-of-sample performance means the cross-validation performance. minimizing your performance on something that is not in your sample that you're using for training by tuning the technique with optimal parameters. Tuning can be performed by cross-validation over a discrete grid of parameter combinations. So for some techniques do not have one parameter. You might have two parameters. So you need to choose all combinations of two parameters, some discrete choices, and see where your cross-validation error seems to the minimum reasonably. And then you choose that as your choice of parameter 1 and parameter 2. That's what this means by grid. So this is something called super learner. I think it would be much ahead to discuss this now. I will discuss this a little later in the future. There's an even more complicated version of trying to come up with an optimal fit. So, also, the problem of classifying class 1 versus class 2 gets harder and harder as the dimensionality of your data set increases. So like the guy asked in the initial point, why is it difficult to find the likelihood, the parameters for the heights of students in a class? It's not that difficult, but if you want to automate it, you need the maximum likelihood process. But so that's the 1D case. But if your data set was getting more and more complicated, this is 2D, this 1D was easy, 2D was a little difficult, 3D is even more hard to come up with a function that separates it. Like this point, separating this red and green is going to be really hard. Maybe it's not possible. So coming up with a function it's not going to be linear regression anymore. Right? Or it could be linear regression, maybe something like this. You would have these many errors though, because you're predicting these as this green class as well. So in these more and more dimensionality, it becomes, if you went from flat world to 10 or 100, or in genomics, you have like 1,000,000 dimensions or like 100,000 dimensions for each row. Because each dimension is a particular gene and you're trying to separate from a cancer patient versus a non-cancer patient and trying to identify how you can do that, predictions and stuff, that kind of stuff. So there it is very impossible to come up with a likelihood, without coming up with a likelihood function, to just, even to plot or visualize that 100-dimensional data set and coming up with what theta of Gaussian is each of my point coming from, or binomial each of my point coming from, so that I have the right distribution. You need to do the likelihood function, maximize the likelihood estimator. Or you need to do the cross-validation for a non-likelihood based technique like SVM or something. But in the end, you need to do cross-validation to figure out what is the complexity of fit. Okay. Yeah.
So when the overfitting or underfitting, do we consider the outliers as well, or we will just exclude the outliers?
Good point. So if the outlier is literally like an anomaly that it is coming up in there as a very low probable point as a definition of an outlier, you should be ignoring it, because otherwise your model will get biased towards the outlier. It's trying to do little good with the outlier as well. But if your outlier was like a small chunk of a cluster, then maybe you have a two-distributional kind of a behavior, like a two-mode behavior. Like if your P of XY, which is generating your data, is not like a single, by mode I mean this. I think maybe you already know what a mode means, but oops, this is a unimodal function. Now, you can see my screen, right? Come on. This is a trimodal function. Yeah. This is a bimodal function. So now the question is, if you have a data set of a lot of points in here and then a smaller chunk of points in here, it's not single outlier or two or three outliers. It's still a smaller cluster. Maybe it's coming from this distribution. This set is coming from this distribution. Then it's not outlier in that case. Then probably you should use it as part of your prediction. You know? The question of whether it's an outlier or not is a different point. But if it was truly an outlier, then you should be ignoring that. You should be removing your outliers before you start fitting the model.
Okay.
Yeah. Yeah. We will deal with whether outlier or not and how to detect feature in some part of the syllabus for sure. So actually, this brings us to the end of the class. So,
hey Praneeth,
yeah.
Quick question.
Please.
So for removing these outliers, we can use quartiles, right? Like the interquartile range, and if it doesn't belong.
It is one way, yes, you can. But there's always a question, you know, how much am I supposed to remove, or what my quartile should be? Do I do the 90th percentile or 95th quantile, whatever it is? That is one way, yeah. Is there a specific reason? I'm just kind of curious why the outside things are coming up in a cluster. Have you had a problem with any of the data set in the assignment or something? Or if it's a good question, that's a really valid question.
Because, like in the recent assignment that we did, right? Like we had a lot of 13 labels, something like that, and we classified a function whether it's diseased or not. So when we use the GLM, when we did the summary, right? When we looked at the summary, we could see there's important variables which have stars. So what I'm thinking is that the specific assignment that we did, the second one, it has some overfitting and underfitting constraints. That's what I think. It wasn't giving a proper result. I mean, we tried.
Yep. The point was to get you into this issue of being able to question for yourself, are you fitting correctly or not, which is great that you brought this up. That was the point of the assignment anyway. Now the third assignment would be the same data set. We can probably change the model we can still keep the same model. The question would be to choose a threshold of your logistic regression output so that, because your logistic regression produces an output between 0 and 1 as a probability. I will write this in the assignment question clearly. You need to choose whether you use 0.5 as the cutoff point of whether less than 0.5 is class 0 and above 0.5 class 1, or maybe use 0.7. That choice is your cross-validation parameter. So what you would do in your next assignment now is you would literally apply cross-validation to choose what parameter gives you the least cross-validation error, and then you would choose that particular one. As far as outlier goes, we're going to deal with that later, though, not yet right away. But I will give you a simple function that will remove some outliers for now.
Because in the last data set, I saw only 2 points were the points of interest for our specific classification, and thinking the rest were just producing some noise in the data.
Yep, these kind of things happen in real life. That's how real life data sets are. So yeah, we're going to deal with it in a step-by-step fashion. We're going to build this towards as if it's a project.
Thanks.
As far as outlier detection goes, there's a lot of literature in there. You can use a lot of different things. So I don't want to bring it up as it's supposed to be a separate lecture by itself. So
yeah, sure. Thanks.
Cool. Yes, so that's the point of this. Any other questions? Okay, cool. So the last slide was just like a cartoon. This, again, coming from some of these books. So it's basically showing the same thing. Which one is, this is training error, this is your tester, that kind of thing, cross-validation error and stuff, overfitting, underfitting. So just the cartoon I put here. This equation is interesting. If this was your linear regression that you're using, you can always come up with constraints on your estimate, on your beta functions. So this is what is known as the lasso technique, where if you had a L1 constraint, it tries to restrict. It's a constraint that is making sure that most betas end up going towards 0. So basically, automatically, it is doing feature selection. So it's a model that will automatically choose what are the subset of features that will do the best in a linear regression setting. I know few people asked how to choose the set of variables in, say, logistic regression. There are ways to do that. We will discuss that more and more in the coming lessons, which subset to choose. But even in here, this lambda is called the regularization parameter. Basically, it's a parameter that is a trade-off between how much I incline towards preserving these constraints of choosing just a few variables, versus how much do I focus on minimizing the error as much as possible. Is this more important? This important? So lambda becomes another tuning parameter now. So you need to choose betas and lambda so that your cross-validation error is the minimum. Then it is automatically choosing just the optimal subset of variables that will give you the least cross-validation error. So cross-validation is a big answer to a lot of your questions, actually. So we're going to do that as part of our next assignment. It's a big thing as part of machine learning in the industry as well. Everyone asks you, what is a training error, tester, cross-validation error, this and that. So
Praneeth?
Yes.
Yeah. So you say it's lambda is something error or something. And as per the Poisson, it says the number of occurrences per interval like that. So what are these terms like? It differs from each concept to concept, or how to remember these formulas? It's really hurdle for us.
I mean, it's very fair statement. You're starting, but I'm sure you'll get better and better over time. Now, yeah, this has nothing to do with Poisson, though. Coming to specifics of the question, this is just a linear regression. This is your loss function, which is this first term is measuring the loss of your linear regression performance. So if I did not have the second term, it's your standard. It's just the risk of your linear regression. So it's measuring your mean square error. So F linear of X is your data, Y is your response, response variable. F linear is your linear regression. L of F linear of X, Y is measuring the error you made at each I, and then you're averaging the errors you made at Ni points by this point. This is your first term. Now, there's a separate technique called lasso or elastic net. This particular one is called lasso, which is linear regression with some constraints on betas. The constraint that this is doing here is trying to make sure that your betas end up becoming closer to zero. Right? Now comes your so there's nothing to do with Poisson in here. Okay, but I get your point. You're bringing up some terms and this and that, and there's a lot of functions and things. So you don't really have to like learn this by heart, but it will become part of you as you keep looking at these equations more and more and try to understand these whole syllabus. So that's the only way to do it. It's also important to be rigorous. You never want to memorize. You also want to, sometimes at one point, so it's like, it's a joke I'm making, but it's going to be a very poor joke, but the point is, even if this were your course of your learning, not the learning of your machine learning model, like your personal human brain learning, right? Anybody's. There is always a trade-off of how much to memorize and how much to really understand. Now, if you want to be the best data scientist or something, right? The person who has the best understanding, at this, which is the least cross-validation error of your human learning, right? At this point, what is going to happen is the point of memorizing this and the point of understanding this, both will become the same. Like you will end up remembering this and you'll also end up understanding every single symbol in this equation. You will know why it is there and you will also remember it, but because you know why it is there. Now that's your optimal learning. So you will get there. In the beginning, you'll be thinking there's too many equations and not able to remember anything. Because then you're trying to think that if you remember, you'd be good enough, but that's not the point. So you want to learn and you also remember. Both will happen automatically as you keep looking at it again and again and working at these things. You will reach this stage where you will remember it, but you will remember it through a process of learning. You won't remember it through a process of trying to memorize it. So it will happen over the time. There's a lot of concepts. You'll keep building upon it. Everything is linked to one another. So don't be impatient. You'll be fine. I think you guys are doing good. As far as your assignments go, you've gone a long way. So I think you're on the right track. I think you will learn a lot towards the end of the course as you keep building up. And sometimes what you learned and what you did not learn in first chapter, you will understand it better in sixth chapter. What you did not, maybe there's 10% you didn't understand in second chapter, you'll understand better in 10th chapter, because what you're learning in the future will keep complementing what you learned in the past. So you'll be fine. All right, so I'll send you the assignments for the next one. Any other questions, by the way? Okay, so, all right, I think we can stop recording the video at this point. The class ends officially at this point. Hemant, do you have any other things you want to bring up?
No, I stopped recording. At least that's what I'm thinking. I think probably it's still recording. That's okay. No, I think this was a good class. I'm noticing that interaction between everybody is increasing. Looks like people have been talking to each other offline, which is great. And I see that this class there's a lot more interaction between Praneeth and the students. That's great. So as always, I mean, if you can reach out to me or Praneeth if you have any questions, and feel free to shoot emails if you have any questions. So I think what we should do is, as part of your assignments, you should all come up with 3 questions, so that we can review them, and that'll benefit all of you guys. So.
Yep, I agree. Point, yeah. Bring it up in the class or before the class or email or as part of your assignment, just like we did last time.
Right. So, hey, thank you very much, Praneeth. And we'll talk to you guys.
Everybody have a good weekend. Sure.